In the last video, we discussed this first technique for evaluating a limit algebraically. And that's just if you have the nice case that you've got a continuous function and you're evaluating a limit at a point in the domain, you just plug in that x value. All right. The second technique that we have is actually going to be just a review of something we learned in the last section. And that's if f of x is a fraction. So I'm just going to write it as t of x over b of x, t for top, b for bottom. If the bottom goes to 0 and the top goes to any non-zero number, okay, if I have that situation, I know I'm going to have a vertical asymptote, which I'm abbreviating here as VA. Okay, so that tells me there are three possibilities for the limit. It could be infinity, negative infinity, or does not exist. And what do? To determine which of these possibilities we have, we do a sign check. Okay, excellent. Now, the third method, and this is what we're going to spend most of our time on here. This is going to be the way that's, well, I guess we didn't know what continuous meant before, but plugging in isn't really a new thing. This is what's going to be a little bit newer. Okay. If f of x is again a fraction, top over bottom. If the bottom goes to 0 and the top also goes to 0, then we cannot conclude that we're in this situation and we have a vertical asymptote. Again, the bottom being small suggests that we should be getting something big, which is what we get when we have a vertical asymptote. But the top being small suggests that we should be getting something small. And so we want to sort of let the top and the bottom fight things out mathematically. Okay. This is what we call an indeterminate form. Just clear up some space here. Okay. What that means is that knowing what the top and bottom are doing individually isn't enough for us to know what the function is doing. So then we're going to do this. We're going to say if f of x and g of x are the same close to a, but not at a, then the limit as x goes to a of f of x is going to equal the limit as x goes to a of g of x, and we'll evaluate this one. Okay. That sounds kind of crazy. So what we're supposed to do is we're supposed to find some other function that's the same as f close to a, but not at a, and then evaluate that limit. So that's our strategy. Find such a function, g of x, and evaluate the limit as x goes to a of g of x. Okay, now that sounds crazy, and how on earth could we do that? We've actually seen that before. So it's going to make a lot more sense, I think, if we look at an example. So let's let f of x be x squared minus 1 over x minus 1. And let's try to take the limit as x approaches 1 of x squared minus 1 over x minus 1. You might recognize this limit. We actually got this in the very first section when we were calculating. This was the formula for the slope of a secant line through a point 1, 1 and a point x squared. Okay. Now here I cannot plug in 1 because 1 would make the bottom go to 0. But I also can't conclude based just on that I have a vertical asymptote. I need to see what's happening on the top. If I tried to plug in 1 on the top, I would get 1 minus 1. That would also go to 0. So I have this indeterminate form. Okay. But what I can do is I can say this is the limit as x goes to 1 of x plus 1 times x minus 1 over x minus 1. All I've done is I've rewritten the top in factored form. And then I can see that I've got an x minus 1 on top and on bottom, so I could cancel that. And then I can say this is going to be the limit as x goes to 1 of x plus 1. Now this function is not the same as this function, because this function would be defined at 1. This function is not defined at 1. But I don't need to record that restriction because I'm not talking about the functions, I'm talking about their limits. And their limit doesn't care what happens at 1, the limit cares what happens close to 1. And as long as x isn't 1, this function and this function are the same. I would be able to say, if I wanted to, f of x is the function, x plus 1, with the restriction that x isn't 1. What I'm saying here, though, is g of x can just be the function x plus 1. That's the same as f, except at 1. Okay. So f, if I were to graph it, would essentially be a line with a hole in it. It would look like so. That's my f of x. G of x is that same line, but with a point there instead of a hole. So what this is saying is if you get an indeterminate form, you're going to hope that the graph of this function is some function with a hole in it. And your g of x is going to be the function without the hole in it. You're going to just fill in that point. Okay? So this right here is my g of x, but now that's continuous and 1 is in the domain, so I can say that's 1 plus 1, so that's going to equal 2. Okay. Now, a couple important things on the notation. Okay. If I'm just working with the function and there's no limit involved, then when I cancel, I need to record that restriction. Because if I change the domain, I change to a different function. When I'm taking the limit, I don't need to record the restriction because I'm using the rule that the limit of this function, that's not defined at 1, is the same as the limit of this function that is defined at 1. They are different functions, but they have the same limit. So it's legal for me to say that the limit of f is equal to the limit of g. Okay, they have the same limit. So with the word limit in there, I can change to a different function and I don't need to record the restriction. If I'm describing a function and I cancel something, I need to make sure that I record the restriction. Okay, the other thing I want to point out is you'll notice that I wrote the word limit at each one of these steps. I dropped it here. I stopped writing the word limit when I plugged in for x. As long as there are still x's in my expression, I need to write that I'm taking the limit. Because the limit, if it exists, is just a number. So I'm saying this number equals this number equals this number equals this number equals this number, 2. It would be wrong for me to say that the limit as x goes to 1 of x plus 1 is equal to x plus 1. That's not true. This is a number, this is a function. So as long as there are x's in there, you got to be writing the word limit each and every time. And I do care that you use proper notation. It's like the grammar that we have here in math. So turning in work with improper notation is like turning in a brilliant essay where you made a wonderful point and used absolutely horrible grammar. And you will be graded accordingly. So do pay attention to what the notation needs to be.